An electric circuit must contain three things: a voltage source, a resistor, and a complete path to connect them. The voltage source supplies energy to the circuit. Batteries and wall sockets are common voltage sources. Resistors transfer the electrical energy from one form to another. They are sometimes called loads. Light bulbs and loudspeakers are examples of resistors. The stronger the voltage source, the more current will flow through the circuit. The greater the resistance or load of the circuit, the lower the amount of current that flows through the circuit. Mathematically, we can state this relationship using a formula known as Ohm's law, written I equals V divided by R. The letter I represents the current, V represents voltage, and the letter R represents resistance. If your circuit has alternating current flowing through it, you will measure impedance, represented by Z, instead of resistance. Resistance and impedance are similar concepts that measure how hard it is for the current to flow through a circuit. If a circuit contains more than one resistor, there are only two ways to connect them: series or parallel. In a series circuit, the resistors are chained together. Like a television series, they occur one after the other after the other. All current that leaves the voltage source must pass through all resistors before it can return to the source. Because of this, the current passing through each resistor in a series circuit will be exactly the same. The current is constant throughout the circuit. Because the current must flow through each resistor, if the path is cut at any point, the entire circuit breaks. This is why one burned out Christmas light takes out the entire strand. They are connected in series. The energy obtained from a voltage source is distributed to the resistors by the current. Because energy cannot be created or destroyed, the total energy converted by the resistors will be equal to the voltage supplied by the source. This is often written mathematically as total voltage equals the voltage of resistor 1 plus the voltage of resistor 2 plus the voltage of resistor 3, and so on. As you add resistors to a series circuit, you force the current to flow through more obstacles. This causes the overall resistance of the circuit to increase. If you need to find the overall resistance of a series circuit, all you have to do is add up the resistances of each resistor. If your circuit has alternating current flowing through it, you should measure impedance instead of resistance. Luckily, the math for impedance works exactly the same as for resistance. In a parallel circuit, there is a direct connection between each resistor and the voltage source. Because of this, the voltage is constant across each resistor in parallel. There are several paths through a parallel circuit that the current has the option to take. Some current will flow through each available path. The majority of current will take the easy way out and flow through the path of least resistance. Regardless of how many paths there are, if you add up the current flowing through each path, it will add up to the total current flowing from the voltage source. This is represented mathematically by saying the total current equals the current through resistor 1 added to the current through resistor 2 plus the current through resistor 3. As you connect more resistors to a parallel circuit, there are more paths for the current to take. This causes the overall resistance to decrease as you add more resistors to a parallel circuit. This is why you trip a circuit breaker when you turn on a microwave, hairdryer, and vacuum all at the same time. Turning on each device connects it to the parallel circuit in your home, decreasing the overall resistance and increasing the current. A circuit breaker trips to prevent a fire. The total resistance of a parallel circuit can be calculated using the formula 1 over resistance total equals 1 over resistance of resistor 1 plus 1 over resistance of resistor 2 plus 1 over resistance of resistor 3. Once again, the math for impedance is identical to that of resistance.